Chapter 16, Part 5, the common ion effect. So when you have a equilibrium reaction of an acid or a base reacting with water, if you add something to that equilibrium, typically a solute, it's going to shift the equilibrium, just like we'd learned in Le Chatelier's principle. So for example, if you have acetic acid in water, you have this equilibrium shown. So if you add sodium acetate, which is going to provide extra acetate ions, you're now going to have extra of this, which is going to shift the equilibrium from what it was to begin with. Now, if we remember, when you add something, it shifts away. So it shifts towards the reactants to use up that extra stuff you added, which is therefore going to use up some of our H3O plus that's in this reaction. And therefore, when you add that, it's going to have less H3O plus, which therefore is going to increase the pH. Okay. So the degree of ionization is going to be decreased because we're going to have less of that H3O plus. And so this is called the common ion effect. So it's typically adding the solute of your conjugate, whatever, base or acid, conjugate base in this case, to your solution. So for example, if we have formic acid, HCH2O, do this. Then our reaction is here. It with water is going to form H3O plus and then your formate. So initially we have 0.025. Initially don't care about water. Initially 0. But then now we are adding sodium formate, which is going to be that ion extra. So we're going to have initially some extra amount, 0.018. So now when we do our icebox, we have to incorporate 108 plus that. It's kind of messy. Into our equilibrium expression. So our K expression is that if we plug in all of the things we know, our Ka, our H3O plus is simply X, but our other numerator is not X. Sorry, plus X. And then our denominator. Now we can potentially simplify this to ignore the plus X and minus X as before, where you would check to see if each of your concentrations, if they divided by your Ka is greater than 100. The first one is. And the second one also is. Okay, so what means we can do is ignore this plus X and that minus X, which is just then going to simplify the math. So when we solve for X, and then X is equal to our H3O plus, so we can solve directly for pH from this. Now what you would find is if you didn't have that extra formate, that 0.018, and you just did your normal icebox, your pH would be less. You would have stronger acid because more of it would dissociate than had you not added that formate. Okay, so a buffer is a type of solution that is very relevant to biological life. So it's a solution that resists changes in pH when you add an acid or a base to it. So it is a solution of two things, some acid and its conjugate base, in varying amounts depending on what the buffer is you're trying to make. So what this does is the two different components have two different purposes. If you add H3O plus, so some amount of acid, it's going to react with the conjugate base that's present. And essentially, it's going to neutralize it. If you add a base, it's going to react with the acid that's present. Sorry, when this donates a hydrogen, this is going to form water, H2O. And same thing here. This is going to donate a hydrogen there. This is going to donate a hydrogen. So buffers are always going to form water. So you're going to pretty much form water, which is going to neutralize it, and then you're just going to regenerate part of the buffer that's already there. So in the first example, you create more HA, which is already part of the buffer, or your base produces OH minus, which is also part of the buffer. So no matter what you throw at it, it can neutralize it. So for example, if you have this buffer solution to some amount of HAs and A minuses, if you add H3O plus, then you're going to just create more HAs, which is already part of the buffer. If you add OH, you're just going to create more A minuses, which are part of the buffer. If you look at these solutions, the one on the left is not buffer, but the one on the right is. So if you add stuff to it, you can tell through indicators whether or not the pH changes. So for both of these second ones, we added OH, and it affected the purple one because it changed colors, but the other one, the pH didn't change, so it's still the same color. If you add an acid to it, it changed the color again because the pH changed, but the one on the right did not. The color stayed the same, so the pH must have stayed the same. So the two characteristics you have to consider for any buffer are the buffer capacity and the pH that it is. So the buffer capacity is how much of an acid or base you have, and therefore how much it can actually react with before the pH does actually change. And the pH is going to be the pH that the buffer works best at, the pH of it itself, so that way it can interact with the other things you add to it and doesn't affect the pH very much. So how do you prepare a buffer? You have to figure out a conjugate acid-base pair based on the Ka of the acid that is as close as you can get to the H3O plus that you are trying to make. And remember, H3O plus you can figure out based on the pH you're trying to make the buffer for. So if we have this general buffer reaction, we have our weak acid and its conjugate base, and this is our equilibrium reaction. Then our acid ionization constant Ka is equal to our H3O plus conjugate base over our starting amount of acid. If we rearrange this slightly to solve for our H3O plus. We will get that. If we take the negative log of both sides, we end up with this new reaction using our log mathematical rules. And negative log of H3O plus, we know what that's equivalent to. That's equivalent to the pH. The negative log of a Ka is something called, just like pH, pKa, minus the log of your HA over your A minus. You can also rewrite this as plus the log and flip those. So put your A minus on top and your acid on the bottom. So we can rewrite this expression with this formula here. So the pH for a buffer solution is equal to the pKa plus log of your amount of base over your amount of acid. This is called the Henderson-Hasselbalch equation, which is just how we can relate pH of a buffer for using the conjugate base and conjugate acid. So if we want to prepare a buffer of a given pH, so we want it to be a pH of 4.90, we need to find a base pair with a pKa close to that. So if we look at acetic acid, this is its Ka. So pKa is negative log is that, which is equal to 4.77. So it's relatively close to the pH that we want it to be. You can create a buffer that's exactly that pH by increasing this plus component, making the log of base over acid larger. And that way, your pKa plus that contribution is going to be equal to the pH that you want the buffer to be. You can also use this equation to solve those common ion problems without having to do an icebox. Makes your life a little easier. Because formic acid is going to be your Ha, sodium formate is going to be your A minus. So pH is what we're looking for. pKa we can find because we know the Ka. So in this case, when you solve pKa, 3.77 plus log of your amount of base over your amount of acid. So this is my amount of base, and then my amount of acid. So if we solve for this whole thing, make sure when you do the log, you do the log of that division. So divide them first and then do the log of it. And you end up getting the exact same pH whether you do the icebox or you do the Henderson-Hasselbalch equation. Okay, so that is part 5 and part 6. I did them together because you can really solve these sorts of problems using either method.